Hello and welcome to the 30th episode of Let's Talk About Electric Vehicles. My name is Teresa, I'm an economist, and together with my co-host Theo, I like to talk about electric vehicles.
Hey!
Hello, Theo. So, as you can probably tell from the title, today we talk about the total lifetime emissions of electric vehicles. But before we jump right into that, we have a little correction to make from last week's episode where we talked about Formula 1, Formula E, and electric car racing in general. So, what's that about?
Yeah, so we had a listener send us some feedback about my description of the regenerative turbocharging in Formula 1. Like we talked about, Formula 1 Formula 1 race cars have hybrid systems, and they have a hybrid regenerative braking system, and then also effectively a regenerative brake on the turbocharger. And I got a little hand wavy about how that works, so one of our listeners gave some really helpful feedback on how to describe that. So I just wanted to quickly talk about that.
Mm-hmm.
So just reminding briefly that the purpose of a turbocharger is to get more air into the engine cylinder so that you can then burn more fuel. And the way that's done is that the turbocharger actually normally runs off of the exhaust gases of the engine. The exhaust gases come out of the engine really hot and fast. That spins a turbine. That turbine, in turn, spins a fan that then pushes cold air, not the exhaust itself, but like other air, into the intake of the engine and allows you to burn more gas, like I said. In the Formula 1 case, they've added regeneration to that. So what they're doing is, on the back end, on the exhaust side, when that turbine is spinning, some of the spinning of the turbine is used to actually charge the battery of the Formula 1 car. And then at certain times, and this is the important part, certain times when there isn't a lot of exhaust coming out of the engine, the turbocharger actually uses a little motor to spin itself and push air into the intake of the engine. The key time that this happens is when you're coming out of a turn. You're racing along, you slow way down, the engine slows way down. The engine then has a lot less exhaust gases coming out, so there's nothing to really run the turbocharger.
Mm-hmm.
But you're about to accelerate, so you need the turbocharger to be spinning, to be pushing air into the engine. And so that motor then uses the battery to spin the turbocharger up and push air into the engine earlier than it would ordinarily have been able to when coming out of the corner. And so you get kind of a win-win. Because you're recapturing some energy, you get better efficiency, and then because you're able to spin up the turbocharger at opportune times, you get better performance.
Thank you, Mike, for explaining this to us. Thank you for listening so carefully, and call us out if we tell some rubbish here. One interesting thing that this particular listener also mentioned, and which I totally agree on, is that the whole event of car racing, of Formula E or Formula 1 itself, produces so many emissions for all of the logistics and such that it's kind of bizarre to talk about sustainability in that context, which I totally agree on.
Yeah, I think my view is a little bit nuanced on that. Like, I think that people living create CO2, and it's definitely worse if they're driving out to the country to get into a big stadium. Although I guess his point was more about also all the moving the cars around from city to city and that kind of thing, right?
Yeah, I mean, everyone at this point can make their own conclusion.
Yeah.
Speaking of emissions, today's topic is the total lifetime emissions of electric vehicles. So what do I mean by that? We all know that an electric vehicle does not have any tailpipe emissions, but when we talk about the life cycle emissions, we also include the emissions of the battery production. This is a highly requested topic by the listeners of this podcast, and I happen to have a bit of experience because I've done similar research in that area, and I'm more than happy to share my knowledge with you today.
It's battery production and also the emissions of producing the electricity, right?
Yes. Oh, yeah, sorry. Exactly. So the thing is, if you're curious about the overall lifetime emissions of electric vehicles and you Google it, you get out very divergent results. So, for example, if I can quote CBC, because I'm Canadian, I quote CBC, they quote a professor from the University of Toronto that says that that an electric vehicle produces 25% more overall emissions than the internal combustion engine vehicle. But then if you go on an article of Clean Technica, you find that a conventional car creates more than twice as much carbon pollution as an electric car. So who can you believe? What's going on? Why are people saying so different things? So there are two reasons. So first of all, the actual results are actually very close. What I mean by that, I'm gonna talk in detail a bit later. And the second reason...
Yeah, but it's not like 10 times off. It's like...
Yeah.
It's close enough that they can reach each other. Yeah.
Exactly. The second reason is that very small changes in the assumptions have a huge impact, can like flip the whole results over easily. So these are the two reasons why you find such divergent results. And to fast forward to the conclusion of this episode, let me tell you that at this point in time, given the number of uncertainties, it is so easy to achieve the desired outcome, so either pro or anti-EV, by still using the most accurate research methods. So what I mean by that is that any researcher has so much freedom in choosing the assumptions that it is impossible to be unbiased when you do such a life cycle analysis, comparative life cycle analysis. What we are going to talk about today is that I will walk you through the different assumptions or the different factors that impact the results and how they impact the results. And then we also have created our own little spreadsheet that enables us to do our own calculation for different scenarios. So I think Theo did something for the US and I have a scenario for Europe at the current technology level. And then we can talk about the future potential.
Right, and that's kind of based on our thinking that electric vehicles have a lot of improvements that can be made, whereas we think that probably gas engines, that they will improve, but there's not as much to be done. They've been evolved for many years and are getting close to optimal.
Exactly. And with that being said, I'd say let's jump right into the assumptions that impact the results of life cycle analysis. When I investigate a study, so when I'm first introduced to a study and I see a certain result, there are actually four factors that I watch out for. I will rush through them and then I will say a couple more sentences about each one. So the first one is the chosen reference vehicles, whether they're really representative for the whole EV sector versus the whole gasoline car sector. The second one is the usage behavior. You have to make assumptions about the total years of ownership, about the annual mileage, and so on and so on. So this is the second big part. The third one is the electricity mix, which is kind of obvious. I think most people do that. And the fourth one is the emissions of the battery production. So let me say a few more words to each of these points. I don't know if you live in Europe, you probably have heard of this very controversial study from Germany by Hans Werner Sinn that finds that electric vehicles produce between 10 and 25% more emissions per kilometer if you include the emissions of the German electricity mix and so of the charging energy, and if you include the emissions of the battery production. So this was very controversial. Especially electric vehicle fans were very outraged, and it was highly criticized. But the thing is, so this study came out around Easter, and when it first came out, I of course redid the whole calculation myself, and I came up with the exact same results. And it's all accurate, all appropriate. The researchers didn't do anything wrong with that calculation. The thing is, you have just so much freedom as a researcher in choosing the assumptions that that is equally justified to, for example, use a different value for the battery production.
So like what assumptions did that paper use that were that kind of took it in a anti-EV direction?
Yeah, so let's take my 4 points. Let's start off by the reference vehicles. They compared the Tesla Model 3 long range with 75 kilowatt-hour battery capacity and compared it with a Mercedes 220 diesel.
In E-Class, I think.
Okay.
Which is like a nice luxury sedan type of thing.
So what comes with the assumptions about the reference vehicle is how do you choose which energy consumption or fuel consumption values you take, because there's a difference between what the manufacturer states versus what is in real life. For the Mercedes, they chose a value of 4.5 liter per 100 kilometers. To be fair, they also chose for the Tesla quite low value, also 15 kilowatt hours per 100 kilometers, which is quite low. What I don't understand is, so what was highly criticized is that you take the Tesla Model 3 long range battery, which is 75 kilowatt hours battery capacity, which is if you multiply it with per kilowatt hour battery production emission value, that really sums up. So this was highly criticized. So again, why not choosing the Tesla Model long range? Why it is definitely
it's a reasonable choice.
It's definitely a vehicle that has high sales numbers, so it's not completely out of the world. But again, you have so much freedom as a researcher. If you were a pro EV, or if you had like an EV favoring bias, then you would probably not have chosen this particular vehicle to compare it.
Yeah, you could choose the standard range plus Model 3, which has a battery that's 2/3 the size, and right there, you'd wipe away the 10 to 20%, likely wipe away most of the advantage that the internal combustion car would have.
Exactly. So this is point 1. So what are the reference vehicles? Second point is the usage behavior. So the electric vehicle has no tailpipe emissions, and it's given the electricity mix, of course, but it typically has just lower operating emissions. But it has higher production emissions. So inevitably, the longer the assumed years of ownership and the higher the annual mileage, the better for the electric vehicle, because it has more time to offset these bigger production emissions.
Yeah, the huge upfront cost.
Yeah. If you want to talk about this German study again, they assumed 15,000 kilometers per year, and they assumed a battery lifetime of 10 years, and then they divided the emissions.
So that sounds pretty reasonable on that one,
but I just wanted to highlight that this has a big impact too. So next, electricity mix. I think this is the one thing that most people think about when they say, okay, it depends. It depends on the location, but so what Theo and I actually discovered throughout the research is that it does not only depend on the particular electricity mix, but also on what is assumed to be the emissions of nuclear. What are the assumed emissions of hydro? What are the emissions of coal production? We find very different numbers for this. I guess it also depends on the particular plant, but so this is also something where the researcher has a lot of freedom to choose these things.
And so what did the German study use?
So they used the German electricity mix, which is quite bad. Ooh, I did not write it down. I
think it was around a half a
I think 0. I don't remember. I think 0.55 kilogram per kilowatt hour.
So speaking of grams and kilograms, I'm American, so I do think in pounds, but we're gonna just talk this episode in grams and kilograms, and you can just think of a kilogram as roughly 2 pounds, and so like 500 grams is about 1 pound, give or take. So on with kilograms.
So this episode is not only a lecture about the total emissions, but also a math lecture, apparently.
Yeah, so thanks for coming.
Feel free. Feel free to calculate yourself. The last but certainly not least important thing is the emissions of the battery production. This is a tough one because we don't really know. There is like a handful of studies that have original data on this, but a handful of studies, this is just not enough to get the whole number of variations that are possible. I'm speaking about the particular battery chemistry. Where's the manufacturer located? This is very important because it's just very energy intensive to produce the battery, and depending on where this manufacturer is located and what the electricity mix is over there, it has a high impact on the overall emissions.
Yep. And I guess on the flip side, there's emissions from the delivery of fuel, the production delivery of gasoline, right, or diesel, and those emissions also vary pretty significantly depending on lots of factors, and so you can have changes in both directions. Yeah,
there's typically a markup of 21% for the production and distribution of gasoline.
Right, but you could live somewhere, like if you lived right next to you lived in Saudi Arabia or something, and the refinery is right next to the pump. I can imagine that fuel having a much lower carbon impact than if you were using Saudi fuel in the United States and refining it in a way that was more or less carbon intensive. Like there's just a lot of variables there.
Yeah.
Like I think 21% is a good average, but if you picked one end or the other, like I've heard numbers where it could be as low as 5% and as high as 40%. Like.
Yeah, this is the point.
Yeah.
And
yep.
Yeah,
and when
you
we say
don't
percent,
really know.
We're talking about as compared to the actual cost of burning the gas. So like when you burn a gallon of gas, it creates X amount of carbon dioxide emissions. And so then what additional percent should you add to that in order to account for the carbon dioxide or equivalent emissions that went into producing that gallon?
Mm-hmm. So lots and lots and lots of uncertainties and lots of different results. The one thing, so I have quite a number of studies that have been investigating exactly this, like how many CO2 equal emissions per produced kilowatt hour battery capacity. And the one thing that I can say is that this number is declining over time. So the older studies tend to have higher estimates than the newer studies.
Oh.
But then there's still studies that came out in the same year, and they have, like the one study has 110 kilogram per produced battery capacity, per kilowatt hour battery capacity, and then another study has like 196 or 195 kilograms per kilowatt battery production. So you as a researcher have the freedom. Yeah, you as a researcher have the freedom to choose the study, to cherry pick your study, which is what, by the way, this German article or this German publication did. So they chose one particular study.
And that study, they chose the 190.
So they have a best and the worst case scenario, and ranging from 145 kilogram to 195 kilogram per kilowatt hour battery production.
Wow.
So it sounds like small decisions, but it sums up. It sums up to the point where you as a researcher have the power to create the result that you want.
Yep. And even like it's not that people are necessarily saying I want this result, but it's just
maybe unintentionally.
There's kind of a subconscious, unconscious bias, and when you're choosing, one study looks a little better to you because you have that bias.
Yeah. And then, of course, it did not include any recycling, whereas, we don't know if you include recycling of battery materials, if you can actually reduce the assumed emissions of the battery production.
Right. Yeah, we'll talk some more about that in the future potential section, right?
Yeah, so that's it for these 4 sections that I look for in a study, and I hope from now on you will too, my dear listeners. And with that being said, let's move on to our awesome Excel sheets, which we will, by the way, provide on Patreon. so you can play around with your results yourself. The last couple of days, Theo and I updated this Excel sheet, and
Yep, we've been in a Excel fun.
So we did a couple of scenarios. Maybe so. What did come out? What cars did you compare, Theo?
Yeah, so I think there were two overall scenarios we did. One was in European, and one was a U.S. example. In Europe, we did the Volkswagen. Basically, the idea was in each example we do a small internal combustion car, and when I say small, I mean
A
small
representative.
from an American standpoint, yeah, which means a representative car in Europe. So a representative internal combustion car, a representative hybrid car, and a representative electric car. And so in Europe, we chose the Volkswagen Polo, the Toyota Prius C, which is the somewhat smaller Prius than the center one, and then a Renault Zoe.
Zoe.
Zoe, what? Am I mispronouncing Zoe?
Okay, I say Renault Zoe, but it's fine.
Oh, well, I think we're both pronouncing it correctly.
Yes. A for effort.
A for effort. And then in the U.S., we're using the larger cars because U.S. cars are generally larger. So the Camry, Toyota Camry Hybrid, and the Tesla Model 3. We're going to use the Standard Range Plus because, our bias. But also the Standard Range Plus is the most popular version of that car. It has enough mileage to get, most people, the vast majority of people will be perfectly fine. They don't need to carry around the extra 20 kilowatt hours of battery to get the long range version.
Bias.
Yeah. We need like a sound effect for bias.
EV favoring bias. I sent an EV favoring bias, yeah. But, well, the thing is, if you don't trust us, you can just download this Excel sheet and then change it to the assumptions that you find make more sense. If you'd
like to get a long range Model 3, please do.
Yeah. Okay, so we were quite ambitious when we started this project, and we also wanted to include a plug-in hybrid vehicle and hybrid vehicles and such. But then, it's very hard.
Yeah, we killed the plug-in hybrid.
Yeah, it's very hard to talk about the fuel consumption and the electricity consumption of a plug-in hybrid because it depends on how you use it, I guess.
Yeah, even more so than with others, because if you just were to always drive your plug-in hybrid as an electric vehicle, then it's almost an electric vehicle.
Yeah, so, but we left the option in there, so feel free to.
And then the spreadsheet. Yeah.
Another difference is the electricity mix. So for the European, we quickly Googled EU average.
I looked at a bunch of states. The states in the U.S., there's a huge variance, and for the U.S. scenario, I picked the median or something around the median. That's a big state, which is Texas, which is about 500 grams per kilowatt hour, so similar to the European numbers. But we can talk more about it later.
Let's stop rambling and talk about the results. So, how many grams per kilometer for the electric vehicle? Do you want to start with Europe?
Yeah, let's start with Europe.
I compared Renault Zoe with VW Polo with the Prius C, and I come up with very, very similar results. Actually, no, not that similar. The electric vehicle is much better. So the electric vehicle produces 92 grams of CO2 equal emissions per kilometer driven, and the internal combustion engine 162 and the hybrid 171.
And that was using kind of the best case assumptions for each.
Yes, these are the best case assumptions for all vehicles. So if there was a range of numbers, then I just took the best one. I also took the worst case, but let's talk about just one case. What's very interesting is that we also created a graph where you can see the actual components of vehicle production, which we, by the way, assumed for all vehicles to be the same. Then the battery production, which is 38. So it adds up 38 grams per kilometer for the electric vehicle and 3 grams per kilometer for the hybrid.
Yeah.
then the charging, and the tailpipe, and the gas production and distribution emissions. Yeah, we will post these graphs on Facebook in our social media channel. By the way, if you don't follow us on Facebook, this is the time where you should check it out.
Okay, so now shall I talk about the U.S. example?
Yes, please.
Okay, so that was so in Europe it was the Zoe and the Polo and the Prius, and so those were, the Zoe was electric and the Polo was gas and the Prius is hybrid. So in the U.S. We did like 3 cars, but it was the electric is the Tesla Model 3 standard range. That's the one with the 54 kilowatt hour battery, and that gets, I think, 200 and some odd miles on a charge. Then our internal combustion car was the Toyota Camry, and then our hybrid car was the Toyota Camry Hybrid. And you notice that all 3 of these cars are bigger than the European cars, and that's because generally cars are bigger in the U.S.
And the other difference is the electricity mix, which is quite clean in Europe. I don't know how many kilograms per kilowatt hour did you assume?
Yeah, so I did some analysis, which we can talk about later, of kilograms per kilowatt hour for each U.S. state, and the variance is ridiculously wide. I picked one that's near the median and is a very populous state, which is Texas, and that's right around 530 grams roughly per kilowatt
which
hour.
is still quite a lot.
Yeah, it's similar to Europe.
So for the Europe average, I had 290 something.
Oh yeah. Okay. Yep. So that's a lot.
290 grams.
But there are certainly states in the U.S. that have much better, and states in the U.S. that have much worse. So we can talk about that. Yeah, same in Europe. More later.
Like Germany has 0.5, as we know, kilogram.
So I think the best thing to do is to, if you're considering buying an electric car and you want to figure out how much CO2 impact it's going to have in comparison to a hybrid or an internal combustion car, just figure out what your personal emissions per kilowatt hour are and use that in your state.
Mm-hmm.
And even some places, this may be a digression, but some places have utility companies have the ability to buy cleaner energy, basically as a way of encouraging them to go out and source cleaner energy from other sources, which then theoretically gives you even cleaner energy yourself. But anyway, the question was...
Lots of variations. Yeah. This is the bottom line.
Yeah. The name of this episode is It Depends. So the Tesla Model 3 versus the Camry Hybrid. In the best case scenario for all 3, the Model 3 had 122 grams per kilometer of CO2. The Camry had 194, and the hybrid Camry had 149. So that's even with the Texas, not so super clean, but kind of middle of the road, the electricity grid mixture. So again, using our numbers, the electric car wins again. The hybrid actually comes pretty close. The 122 versus 149. Again, not a huge difference, but it is a difference.
Yeah.
Okay, so what's next?
Then we have not talked about potential, because this is what really is a reason to implement more electric vehicles, because the electric vehicle has so much more potential for lower emissions versus the potential for the internal combustion engine is just like there are still improvements in technology, but it's nothing in comparison to the potential of technological progress in the electric vehicle technology.
Yep, for sure. Yeah, so the kind of the areas of potential improvement that are out there. I mean, one is that the car itself can get more efficient. That's probably not the biggest improvement, and as Teresa just said, like gas cars can also get somewhat more efficient, just in terms of like the shape of the body and how efficient the motor is. The same thing can happen with electric. So that's one potential area of improvement. Another is that the battery production process can become less CO2 productive. I think Teresa, you mentioned that there's a number somewhere around 60.
Oh, yeah. So, but I forgot where I read this. But someone estimated once that you can minimize the emissions of the battery production to 55 kilogram per kilowatt hour battery capacity production, which is like really an estimated bare minimum if you're super efficient in your production.
Gotcha. So that's from raw materials.
Right
still.
now it's right now it's estimated between 100 and 200.
Okay. And we were, So that's one, like you can imagine that even if we got down to 75 from our current 100 to 200, that's still at least 25% decrease in the amount of CO2 being emitted during the production of the battery, which would equate to a pretty big savings in the total lifetime or per kilometer CO2 emissions of the car, of an electric car. So, battery production, a pretty significant potential improvement. Another one that's related is the reusing or recycling of the battery material. After the battery has been in use for 10 years and it's not performing as well as it did when it was new, first of all, it still might be useful. It's something that might be useful to put on the grid and use to store energy on the grid. And in that case, you should basically be able to count that the CO2 savings of storing that energy on the grid against the original cost of producing the battery. Cost, again, in terms of CO2. And of course, it depends, as like everything in this episode. Like, if you're storing energy on the grid with these reused car batteries, is the energy you're storing actually clean energy? If you're storing dirty energy, then you're not really saving any CO2. It's certainly possible.
Speaking of clean or dirty energy, I think the biggest potential is the electricity mix.
Yep, I agree. So especially in certain areas that they're just burning coal, right? Coal emits a ton of CO2.
Alberta.
Teresa's coughing because she's been breathing too much coal dust when she was growing up in Austria.
Austria has a very clean electricity
No, but doesn't the coal blow over into Austria?
Is this how it works?
Anyway, maybe there are other reasons why she's coughing.
Since we're talking about clean energy, so the reason why Europe has such a clean energy average is actually because of all of the nuclear from France.
Oh, interesting. So if you're in France and you have an electric car, you're emitting very little CO2, but you're emitting nuclear waste.
Maybe talking about the pros and cons of nuclear is that will go beyond the scope of this episode.
Yeah, that might be another podcast. Let's talk about nuclear
That's not
reactors.
Controversial.
Anyway, so yes, cleaner electricity is absolutely something that's going to happen, and is probably the biggest improvement that will come in electric vehicle CO2 emission equivalents. And so there's no. It's really hard to say how quickly that's going to happen, but there's no question that it's going to happen, and that's really one of the things that makes electric vehicles, in my mind at least, a no-brainer.
Shall we make before we end this episode? Shall we take a scenario and go crazy with the assumptions and type in a futuristic scenario and then say what the results would be like?
Yeah, sounds good. But
sorry.
First, there's one more thing I want to talk about on potential, or two more things. One is that you can reuse the batteries potentially for storing grid energy. You can also just straight up recycle them and get the raw materials out. And if you were to be able to get the raw materials out and the recycling process was not too carbon intensive, which I would expect is at least possible, then you could save tens of percents of the production CO2 emissions from the battery when you're building a new battery. And so you can basically look at that as the battery production CO2 emissions going down, let's say by 20% or something, which then makes the EV significantly more CO2 efficient. And then finally, more on batteries. Batteries can just get better, right? They can get better at storing energy. They can last longer. They can be more efficient to charge. All these things will have little effects on the efficiency and will be in the positive direction for electric vehicles. So yeah, let us come up with a crazy example that is the best. Future 10 years from now. Oh my god.
So I want
celebration.
90% renewables. Can we do that? Can we do 90%? Can we do 90%
is this like
wind?
A bidding war type of thing? I think we probably want to have a mixture of wind and solar, but we're going crazy here. Do what feels good.
10% hydro. No.
So this is
10% 10%
natural
I'm trying to
think
gas.
about where this country
is. What I
is.
know about renewables is not much. No, I know a little bit about renewables, and I know that it makes sense to have a natural gas plant, even if you go up with renewables very high. But the advantage of natural gas is that you can turn it on very easily and very quickly versus, for example, a coal plant. It takes a long time till it runs. So just in case.
Yeah, actually, that's a specific type of natural gas plant that they're called peaker plants, and they're relative to other natural gas plants. They are bad for carbon emissions, but they can be spun up very quickly,
which can be very useful if you have these volatile renewable generation going on.
Yep. Although, if you take all those used EV batteries and put them on the grid, then they can store the wind energy.
True.
And then you don't have to have any peaker plants.
True.
But we have to make some assumptions. So yeah, let's say 90% wind and 10% gas.
Yes,
just
this
as
is
a really good.
I plugged in already. I was very eager to type that, and I also assume. So we have to change something with the CO2 equal per kilowatt hour battery production. I'm going to assume maybe 60 kilogram.
Oh, that's too good. Let's say 65.
65. Oh, yeah, because that makes all the difference. Because
the optimal... Okay.
That's too good.
70?
Are you kidding me?
It's 5 kilograms, but it's twice the distance from optimal, so... It's a significant.
If this is the real optimum, okay. I typed in 65.
Okay.
What else do we
are we changing?
The battery. Do we change something with the specs of the vehicle? The fuel consumption.
Yeah, I don't expect that to get a lot better. I mean, I think that. Let's just leave it as it is.
Maybe the total lifetime of the battery. Oh no, did we? Yeah, battery lifetime.
Yeah, we did.
We have 150,000 kilometers.
Yeah, let's up
200
that to 300.
Ooh,
300.
I like that.
Take that.
I'm already looking over to the results. It's giving me a lot of satisfaction.
Yeah. What else? I think that's it.
Yeah. Shall we talk about the results? So I did it for Europe.
Okay.
But, I mean, it doesn't make it... So I did it for the European vehicles. This is the difference. And you did it for the American vehicles, I guess.
Well, let's just talk about the European. So the previous... Before you made these changes, the EV was at what?
I think 92... I don't remember.
92 grams per kilowatt. Sorry. Grams per mile. Per kilometer.
Per kilometer.
Okay. And so then, how does it look now?
So now it's 41 grams.
Nice.
And the total lifetime over 9 years, total lifetime emissions are 7.3 tons versus 21.9 tons for the gas vehicle.
Yeah.
Which is 3 times as much. Maybe, so I haven't really explained what I mean by CO2 equal, because that might be a bit confusing. What I mean by that is that not all of the emissions are necessarily carbon emissions. There's also methane. What's it called?
Methane.
Methane, and some other emissions, and there you can convert them into CO2 equal.
And methane, for example, is much worse than CO2. So if you emit a little bit of methane, that counts for, I don't know, a ton of CO2.
Yeah.
Okay, so basically what we're saying here is that in the future, you can argue with the specific numbers we used, but there are a lot of ways that electric vehicles can get better in terms of CO2 emissions or CO2 equivalent emissions. And when you apply those ways to existing models, it makes it clear, like EVs might get twice as efficient, which is this huge improvement, whereas gas cars make it somewhat more efficient, but not twice as.
Yeah.
I think one thing that we didn't give a lot of discussion to is hybrids, and they're a difficult case because they kind of have some of the benefits and some of the downsides of both. And I certainly, you can look at plug-in hybrids, especially plug-in hybrids, like can basically be electric cars and they can be gas cars. And I personally think that plug-in hybrids are going to be a big part of the automobile sales over the coming years because of that.
Do you think, like as a transition, or will they just replace gasoline cars, and there would just be no gasoline cars but hybrid and fully electric? Or how did you think that this will further?
Yeah, I see
develop?
I see it that way, that there will be more and more plug-in hybrids on the road, and that they will tend to replace gas cars. But I think it's hard to say. Like they will also take a segment of the electric car market, people who have a little more serious case of range anxiety or more need to be able to sometimes go a long way.
What about the enhancing battery technology? What about, for example, solid-state batteries? I don't know. I personally don't have a lot of faith in hybrid cars, but we've talked about this before. I'm just not a big fan of hybrid cars. I think that they combine both disadvantages. The disadvantages being having tailpipe emissions and being just a complex vehicle. And I see them as a transitional vehicle, but I don't see them as long-term solution. But yeah, I know that your opinion is very different, and I'm pretty sure that most of the listeners are what is she talking about? I'm sorry.
Yeah, but
no hate.
It's I think my differing perspective is based so on the tailpipe emissions is based on, well, they can be clean, right? If you basically, they give people the ability, especially plugins, give people the ability to be clean when they want to, like plug in when you want to, and then if you want to spit out the CO2, you can go do that too. And then from a complexity standpoint, I think the impact on the price is really the biggest issue to me with complexity, and that's very obvious. Like, those cars are expensive. You're buying a small electric car and a gas car at the same time. Like, it's got a lot of parts. But from an actual maintenance standpoint, there's enough historical data to show that those cars are quite reliable, and that maintenance it's very similar maintenance costs when you consider the fact that the electric system takes load off of the engine and takes load off of the brakes, and therefore makes those last longer.
Yeah, but we both know that the cost is what really matters.
That's true.
Not the maintenance.
You mean the upfront cost?
Yeah, the upfront cost.
At least really matters in terms of whether people will buy it. Yeah, it's a big factor. So yeah, we'll, of course, the answer is it depends, and we'll see.
Yeah, I think we have to postpone this discussion about hybrids to another episode where we will solely focus about hybrids. Yep. Maybe this will be fun, like having different opinions about it and.
Yep. Yeah, we can do a real debate.
This is for the future.
Yep.
Speaking of future, the future is that we are going to end this podcast episode.
Yeah, at some point, today.
Yeah, thank you so much for listening. I hope that you learned something new and that you have a lot more arguments and statements for the next EV discussion with your friends.
Yeah, or if you're an ICE enthusiast, you'll have more ability to parry EV arguments by saying it depends.
Yeah. One thing to remember is always look at the assumptions. Never just take a result for given. That's the most important conclusion. Always look at the assumptions.
Yep.
Thank you so much for listening. Thank you for listening all the way through. This has been a long episode. And I would like to particularly thank our patrons on Patreon for the support, and you will find the results that we've been talking about here on Facebook, and you will find the spreadsheet on Patreon. The links are in the show notes, as well as all of our references. And yeah, I'm very much excited to talk about electric vehicles again soon.
Me too. Thanks everyone for listening.
Okay, have a wonderful week and
have a good week.
Bye.
Bye.